Welcome to this segment of our lecture series on quadratic equations, inequalities, and quadratic functions. Now we are starting with quadratic functions, and for lesson 3.9a, I will be discussing the definition of a quadratic function, the forms of a quadratic function, and the properties. Okay, so let's start with the definition of a quadratic function. Okay, here we have for any a, b, c element real, a not equal to 0, this equation f of x equals ax squared plus bx plus c defines a quadratic function. Okay, and we can write a quadratic function in several forms. The first form is this one here, f of x equals ax squared plus bx plus c. This is our general form. The next form here is, let's say, a times x minus p times x minus q. Here we're given x equals p and x equals q, the intercept form. And the next one, f of x equals a times x minus h squared plus k. This is the standard form for our vertex form. Okay, so we can identify our quadratic function by any of these three forms. Okay, now we can set our properties now of a quadratic function. Number one, if you look at this form here, f of x equals ax squared plus bx plus c, the graph of this is a parabola that here opens upward or concave upward if a is positive, and the parabola opens downward if a is less than 0, or it's concave downward if a is less than 0. So, for example, we have here, this is a parabola that's opening upward, therefore a here is greater than 0. And for this one here, it is opening downward, and we say a is less than 0. May I ask the question, why may a not be equal to 0? And we have known that previously, that if a is 0, then we don't have a quadratic function, we only have a linear function. That's why in our definition, we specify that a should not be equal to 0. Number two property, we can get from this form here that the vertex coordinates are h and k. Okay, h and k, and this vertex will either be the lowest point of the graph or the highest point of the graph. And number 3 here, this vertex here, the x-coordinate of that vertex will split this graph into 2, which are symmetric with respect to that line. So we have an equation of axis of symmetry is given by the x-coordinate of the vertex. So x equals h. Okay? Now, if the parabola is going up, we have a minimum value of the function, which is the y-coordinate of the vertex. So here, number 4, the value of the function at h equals k is a minimum value if a is greater than 0. And this one becomes k becomes a maximum value if a is less than 0. Erase this now. I can now discuss the domain and the range. If you look at this equation here, there's no value of x that's excluded. That means here x is element real. So for any quadratic function, your domain is x element real. However, the range is based on here, the value of the function at h equals k. Here, if you have a projection of your graph to the y-axis, you will notice that your lowest value for your function is k. So therefore, the range for this function here will be starting from k up to positive infinity if the parabola is opening up or a is greater than 0. However, with this case here, hk here will be the highest point, then your reflection or your projection of your graph will just be found going down. So our range for this one will be starting from negative infinity up to k. So negative infinity up to k. That is if a is negative. Okay? Now, the graph of f of x is actually the graph of g of x equals ax squared. The graph of f of x is the graph of g of x equals ax squared translated horizontally h units and vertically k units. So we can glean that from this form of the quadratic function. We can move by h units along the horizontal line and k units vertically. Okay? Now, the next one. The next property involves the discriminant of the given function. If you will remember this is actually the discriminant of the quadratic equation ax squared plus bx plus c equals 0. This one here describes how many intercepts will our function have depending on if first one d is greater than 0, then what do we have here? There are 2 x-intercepts. Okay, these are two x-intercepts. How does the graph look like there? You can either have here a quadratic function graph going up here and it is going to intersect the x-axis in 2 points. let's say these are your intercept here, P and Q. Okay? Or you can have something that goes down there. In the same manner, this one is my P and this one is my Q. So two intercepts, x-intercepts. Okay, and the next one, if D equals 0, then there is one x-intercept. Okay, how will our graph of that look like? Its graph will be a parabola that has its vertex on the x-axis. So this one here has a vertex on the x-axis. I can have something that goes down and the vertex is there. So if we speak in terms of ax squared plus bx plus c equals 0, the roots of this are real and equal. Whereas this one here, the roots of this are real and unequal. So we are now talking about the roots, okay, of the related quadratic equation. But I'm concentrating on the discriminant. Suppose the discriminant is less than 0. If the discriminant is less than 0, then there is no real x-intercept. In terms of the graph of the quadratic function, either you have your graph above the x-axis or you are below the x-axis. Okay, so in terms of this quadratic equation, the roots here of this quadratic equation are imaginary. Okay, which means the graph will not touch the x-axis. Now, let us see here that I am now talking about this quadratic function ax squared plus bx plus c. Okay, where if I equate this to 0, if y equals ax squared plus bx plus c is equated to 0, then I actually have that quadratic equation here. And we know the solution to this is given by x equals negative b plus or minus square root of b squared minus 4ac over all over 2a. So I can get here two roots. These roots here that I get, I will term them the zeros of this function. Okay, so zeros of the function are numerically equal to the roots of the related quadratic equation. Okay, so we can interchange the zeros and the roots. But for as long as we're dealing with functions, then we call the roots of this quadratic equation the zeros of the quadratic function. So there we have it. We defined our quadratic function as this one here, y equals f of x equals ax squared plus bx plus c, where a is not equal to 0 and a, b, c element real. And we term this as the general form of the quadratic function. The other form was the intercept form, where here we can identify what makes this expression on the right equal to 0 will be P and Q. They're actually your x-intercept of the graph. And the last form that we have is this form here, where the vertex is at HK. Here ends the first part of our lecture on quadratic function. See you in the next lecture.